In this lesson, I really want to focus on how to describe matrix multiplication as acting on the columns of the matrices involved. We will go through several statements where I explain what that means. In the previous lesson, we defined matrix multiplication coordinate by coordinate, where we said the standard way to think of multiplying two matrices is to pairwise multiply rows from the matrix on the left with columns from the matrix on the right. So that's a very quick summary of what we talked about last time. And what we ended with was this boxed statement I have here, saying that if you take a matrix A and multiply it by standard basis vector, the result will be the jth column of the matrix A. So let's pick up right there where we left off. We will use this fact to better understand how we can think about a matrix multiplying with a vector. That will lead to another way to think of the product of two matrices. And at the end, we will actually return back to this fact to put together some kind of famous celebrity matrices, if you will. So our key fact here is that if A is an M by N matrix and EJ is the jth standard basis vector in Rn, then AEJ will be an M by 1 vector and it will be the jth column of A. Let's give that column a name. We'll call it A sub j. Notice it's a vector in its own right. And if A is M by N, so that EJ is N by 1, this column will be M by 1. We look to the outer dimensions for that. Okay, let's think about how A would act on any other vector in Rn. To do this, think of the vector x as consisting of the coordinates x1, x2 through xn, as I've labeled here. And notice that this vector is the result of actually taking the standard basis vectors e1, e2 through en, scaling each one by x1, x2 through xn respectively, and adding that together. x1, e1, for example, would be the vector x1 followed by zeros. x2, e2 would be 0, x2, 0, 0, 0, 0. And with this recognition, we piece back together the original vector x. So my note here points out that each x sub I is a scalar. It's the coordinate in the ith position of the vector x. And then for the matrix A, I'm not going to think of this as an M by N grid of individual coordinates as we've done in the past. Instead, I'm going to think of A as N columns stacked side by side. So the first column of A is the vector A1, the second column of A is the vector A2, through the final column of A, which we'll call the vector A sub n. Let's now investigate what it means to compute the product of A and x. I've put the entire computation here, but let's go slowly through this. So my first step is to take x and replace it by this new representation where we've broken it down as its own coordinates times the standard basis vectors. Matrix multiplication is distributive and scalars pull out. So on the second line, I have distributed A to each of these terms and pulled the scalar xi in front. But now notice that AE1 is the column A1, AE2 is the column A2, and we continue that until AEN is the final column AN. So we can think of the matrix product A times X as what we call a linear combination of the columns of A. The set of all such linear combinations is called the column space of A, denoted with this col A notation. And notice that idea of the set of all possible linear combinations of the columns of A is kind of like saying all possible results of doing A times X, where X is in Rn. That would include, for example, A times the 0 vector in Rn, as well as A times every other vector in Rn. Let's take a look at a specific example. So consider this 4 by 2 matrix multiplied on this 2 by 1 vector. So the 4 by 2 matrix is the matrix A, and the 2 by 1 vector is the vector X. In the previous video to multiply this, we would have taken the first row of A and multiplied that with the entries of X. Looking at this, we realize that the result will be a 4 by 1 vector in R4. So we are looking to compute 4 coordinates. And in the last video, what we could have done is say that the first coordinate is 4 times 3 plus -1 times 4. So there I looked across the first row of A and matched those entries up with the entries of X. But now what I would like to do is recognize that this product can be viewed as a linear combination of the columns of A, where the scalars that we are scaling the columns with are the entries 3 and 4 from the vector x. You could also call those the weights. That word has meaning in certain context. This is going to lead to the same result, it's just the algebra will feel a little bit different, so we can scale those two vectors and then add them together to get our final 4x1 result, which is, as we said, a vector in our 4. And now specifically, I can identify it as a vector in the column space of the matrix, because it can be represented as a linear combination of the columns of the matrix A. So hopefully this example makes it clear why a matrix times a vector can be viewed as a linear combination of the columns of the matrix. Let's go a little further. Now suppose that A is an M by N matrix and B is an N by P matrix. We can multiply A and B to get an M by P matrix, and then what if I wanted to say something about the jth column of the resulting matrix? Well, now we know that we could take the matrix AB and multiply it with the standard basis vector EJ. And what this product should give us with EJ is the jth column of AB. If you haven't identified the dimensions of EJ yet, let's just pause to identify the sizes of the matrices that we're multiplying. So we know that A is M by N, B is N by P, therefore EJ must be P by 1. It is a vector in RP. To say more about this jth column of AB, let's use the associativity of matrix multiplication. So I can think of this as the matrix A times BEJ. But now observe that BEJ is going to be the jth column of the matrix B. It is, as expected, an M by 1 vector, so that now we can say A times B sub j is the jth column of AB. The conclusion of what we've just computed is that if you want to take two matrices A and B and multiply them, instead of proceeding with coordinates like we did in the previous video, we can think of the matrix product AB as A acting on each of the columns of B. In other words, the matrix product AB has columns that look like A times the first column of B, then A times the second column of B, all the way through A times the last column of B. I have a challenging question here. Let me explain what I'm asking, and then I would like for you to pause and think about it. We said that the set of all possible linear combinations of the columns of A was a set of vectors that we call the column space of A. Analogously, looking at this new matrix that we formed in the bottom right, we could consider all possible linear combinations of those columns. Call that the column space of AB. I claim that it's either the case that the column space of A is a subset of the column space of AB, or vice versa. The column space of AB is a subset of the column space of A. What it means to be a subset here is every linear combination that you could find on the left could also be found on the right. So is it the case that any linear combination of the columns of A could also be thought of as a linear combination of the columns of A times B? If that's the case, then the first proposal is correct. Before I let you go, here's a hint. I recommend that you write down a linear combination of the columns of AB. Those are the columns that we have in the bottom right corner of our computation here. Just write down what a linear combination of these columns would look like and just see what you can do with it algebraically. Make sure that you are observing correct properties of matrix multiplication. See if you can arrive at one of these conclusions. Okay, go ahead and pause and make of this what you can. All right, I hope that you were able to arrive at one of these two conclusions. Here's the answer. It turns out that the column space of A times B is a subset of the column space of A. And let me show you how you could get to this. Following the hint, we can create a representative linear combination of the columns of AB by taking those columns and creating a linear combination out of them. So here I have new scalars C1, C2 through CP, so that any kind of combination of the columns of AB can be written as C1 times the first column, which we know to be AB1, plus C2 times the second column, which we know to be AB2. And then we keep doing that until we've reached at CP times the final column, which we know to be ABP. If you wrote down this kind of construction, what I hope you were then motivated to do is factor that A out in front. And that would be correct. Let me throw in some extra notation here. We can think of these weights, C1, C2 through CP, as entries in a vector C. Notice here that I am saying that C is a p by 1 vector. I'm writing it as a row vector transpose so that it's actually a proper column vector. Then let's do the most natural thing that we can looking at this linear combination and factor A out front. This operation makes sense because we know that matrix multiplication is distributive. Now if you look at what's inside the parentheses, we have a linear combination of the columns of B. So it's the columns of B scaled by these weights, C1 through CP. But that is exactly what it would mean to do the matrix product B times the vector C. That's what we discovered when we looked at A times X a few minutes ago. But I claim that A times B times C is actually a linear combination of the columns of A. Stick with me for another minute, and here's the reason why. BC will be a vector in Rn, which means that we are doing A times a vector again, just like we did A times X. So A times B times C will again be a linear combination of the columns of A. Since it's a linear combination of the columns of A, the result belongs to the column space of A. As any linear combination in the column space of AB can now be thought of as belonging to the column space of A, we conclude that the column space of A times B is a subset of the column space of B. This was a little bit more advanced than some of the exercises that we've done so far, and you might need to watch it a couple times for it to really stick. What I'm hoping to underscore with this demonstration, though, is that when you take a matrix and multiply it with a vector, what you are producing is a linear combination of the columns of the matrix. That's the most important message here. Since this exercise was a bit theoretical, I thought it would be fun to end this lesson by doing some specific, very concrete matrices. We have been looking at matrices as rectangular arrays of numbers without giving them a lot of meaning. So in this exercise, I also want to communicate the idea that matrices can transform space. That is an interpretation that we can revisit later. But for now, let me just tell you that these 5 transformations on the xy plane that I've listed here can be described as the action of a matrix multiplied on vectors of coordinates in R2. I'll give you a visual example of what I mean in just a second. For each of these descriptions, we are going to deduce what the right 2x2 matrix is because we know what the columns of the 2x2 matrices need to be. They need to tell us how each of these actions moves the standard basis vectors E1 and E2. So we are returning to that idea that we opened with, which is that A times the standard basis vectors gives you the columns of A. So we are going to figure out what the columns of A need to be. Let's start with the transformation that is reflection over the x-axis. Okay, so here's the xy plane. I've got the x-axis and the y-axis. Let me add to this picture vectors which represent the standard basis vectors. So E1 you want to think of as the vector 1, 0. To represent that vector visually, we start at the origin and we end the vector at the point 1, 0. And then similarly, E2, the standard basis vector 0, 1, we will represent visually by starting at the origin and ending at the point 0, 1. These two vectors are position vectors for the points 1, 0 and 0, 1. To reflect the entire xy plane over the x-axis means to flip it like this. After doing that, I can see what happened to E1 and E2 under this flipping action. So in particular, AE1 is just going to be E1 because E1 didn't move. However, AE2 is going to be 0, -1 because it flipped. And that's enough. With just those two pieces of information, I can tell you what the entire matrix, which represents reflection over the x-axis, should be. In the first column, we have 1, 0 because that's what happened to E1. And in the second column, we have 0, -1. That's what happened to E2. To check that this matrix makes sense to you, imagine taking the coordinates of any other point in the xy plane. For example, consider the position vector 3, 4, which starts at the origin and ends at the point 3, 4. If you reflect that over the x-axis, it's going to flip down to 3, -4. And that's exactly what would happen if you did this matrix times 3, 4. You would get back 3, -4. Based on that example, take a second to write down the matrix which would reflect R2 over the y-axis. Okay, again, it's going to be a 2 by 2 matrix, but this time E1 is going to flip to -1, 0. So that's the first column of this matrix. E2, however, doesn't move. Since it lies on the axis of symmetry, E2 will just get mapped to E2. And then again, you could take this matrix and multiply it with any pair of coordinates you like, and you'll notice what happens is that the x coordinate gets flipped and the y coordinate stays the same, and that is indeed what it looks like to reflect the xy plane over the y-axis. Okay, let's similarly talk through the idea of projection onto the x-axis. So to project the xy plane onto the x-axis means to basically crush it flat onto the x-axis. So everything just gets sent straight down or straight up to the x-axis. Thinking back to the E1 vector, what happens if we try to project E1 onto the x-axis? Well, it's already there. It has no change. So the first column of this matrix is 1, 0. Now picture E2 lying along the y-axis. If you project E2 onto the x-axis, it's going to get crushed down to the origin. So the second column of this matrix is 0, 0. This 2 by 2 matrix should encode the action of projecting onto the x-axis, and once again, if you take this and multiply it by, say, 3, 4, you will get 3, 0. Take a moment to work out the 2 by 2 matrix, which we could use to project all of R2 onto the y-axis. And once again, it's the same idea. Starting with E2, which lies along the y-axis, nothing really happens to it. So E2 gets mapped to E2, but E1 gets crushed to the origin. And if you take this matrix and multiply it by any vector with 2 entries, what it will do is zero out the x-coordinate and preserve the y-coordinate. So that is projection onto the y-axis. Let's finish with one of my favorite 2 by 2 transformations. This is rotation by angle theta. So when you picture that, you want to imagine rotating counterclockwise in the xy plane, where theta is measured off of the positive x-axis like I've pictured here. We can recognize that E1 had unit length, so to get the coordinates for that arrow on the right, where E1 has moved after rotation by theta, we can just think about, say, the coordinates along the unit circle and recognize that the coordinates of that point are cosine theta, sine theta. So the vector cosine theta, sine theta is the vector which starts at the origin and ends at that point. It's the position vector for that point. The other vector is a little harder, but again, if I want to think about, say, the unit circle, how far have we rotated from the positive x-axis? We've rotated theta and also 90 degrees, or pi over 2 radians. So the coordinates where we've arrived at are cosine of theta plus pi over 2, sine of theta plus pi over 2, which using angle addition laws will give you negative sine theta cosine theta. So the vector negative sine theta cosine theta is the position vector that starts at the origin and goes to that point. Now we can put this together to arrive at the well-known 2 by 2 rotation matrix. The first column is cosine theta sine theta, because that's where E1 has been rotated to. And the second column is negative sine theta cosine theta, because that is where E2 has been rotated to. So by just thinking about those two vectors, E1 and E2, and figuring out where these transformations move them, we can actually put together a 2 by 2 matrix, which could then be multiplied with any vector in R2. Okay, that wraps up this lesson. I hope that you enjoyed this column-based look at what it means to do matrix multiplication, both a matrix on a vector and a matrix on another matrix. Thank you for your attention.